Okay, let's unpack this. You see HTTPS in your browser bar constantly, right? That little padlock icon. Most of us interact with it every single day without truly understanding its magic or what it's actually doing behind the scenes to protect your data. Have you ever wondered what makes that little padlock appear?
It's fascinating, really. HTTPS acts as this invisible guardian, almost like a silent partner. It ensures privacy, integrity, and trust every single time you interact with a website. It's truly foundational to how we use the web today. So our mission in this deep dive is to try and transform this, seemingly complex topic into something clear, understandable, and hopefully deeply insightful for you. By the end, you won't just be seeing the padlock, you'll understand the intricate layers of security it represents. And our main source today, HTTPS Essentials, Interview Questions and Answers, gives us a really fantastic framework for understanding these core concepts from the ground up. It's ideal for anyone wanting to be well informed about this absolutely critical internet security layer.
Okay, great. So let's start with the big picture then. HTTPS, it's essentially the secure version of HTTP. Can you walk us through the fundamental differences? What really makes it secure? What's the core distinction there?
Absolutely. The core distinction, the magic, as you put it, well, it's that HTTPS uses SSL, Secure Sockets Layer, or more accurately, its modern successor, TLS, Transport Layer Security.
Yeah.
It uses these protocols to encrypt the data flowing between your browser and the web server.
Okay, encryption, so hiding the data.
Yes, hiding it. But it's more than just that. This encryption provides three absolutely crucial guarantees. First, confidentiality, like you said, keeping your data private, unreadable to snoopers.
Right.
Second is integrity. This ensures the data hasn't been tampered with or, altered while it's in transit.
Ah, okay, so it arrives exactly as it was sent.
Precisely. And third, there's authentication. This verifies the website's identity using digital certificates. We need to know we're talking to the real website, not an imposter. And the genius here isn't just that these three pillars exist, it's how they work together, how they intertwine, really, to create this bedrock of trust. I mean, billions of dollars, trillions of personal interactions rely on this daily.
Yeah, I can see that. You wouldn't want to log into your bank if you weren't sure.
Exactly. If you couldn't be absolutely sure no one was reading your password, or worse, that you weren't even talking to the real bank. It's this combination that builds the invisible trust network of the internet.
Okay, I see. So it's not just encryption, but also making sure the message hasn't been fiddled with and that you're talking to who you think you're talking to. That really hits home. And practically, just for, everyday browsing, what are the obvious tells? How do I know if a site is using HTTPS versus just plain old HTTP?
Good question. Yeah, the practical differences are pretty clear indicators once you know what to look for. First, you'll see it right in the URL prefix. It'll be HTTP for insecure connections and HTTPS for secure ones. That's literally, it stands for secure.
Simple enough. The S means safe.
Pretty much.
Huh?
Secondly, there's the port number. HTTP usually uses port 80 for communication, whereas HTTPS switches to port 443. You can think of it as like a dedicated locked entryway just for secure traffic.
Oh, a different door number.
Right. And crucially, HTTP doesn't require any special certificate, but HTTPS absolutely does. It needs an SSL TLS certificate to enable that encryption and verification we talked about.
Got it. Certificates are key.
Absolutely. And about SSL and TLS, it's worth noting that TLS is really the modern, updated version of SSL. Think of TLS versions like, I don't know, different generations of a secure language, TLS 1.0 and 1.1. They're like old, easily cracked codes now. So browsers have largely stopped speaking them.
Obsolete, basically.
Yeah, deprecated. TLS 1.2 is sort of the common tongue for now. But TLS 1.3 is the latest, fastest, and most robust version. It's like a brand new, highly efficient secret language that modern systems are increasingly demanding for all their communications.
So if my browser and a website are trying to talk securely, they need to agree on the same up-to-date version of TLS or the conversation just won't happen securely.
Exactly. They need to speak the same secure language. And all these features, they directly protect your sensitive information. Think about your login details, credit card numbers, any personal data you type into a website.
Yeah, stuff you definitely don't want floating around.
Right. Without HTTPS, that information would be sent as plain text, totally vulnerable to anyone who might be eavesdropping on the network. With HTTPS, because of the encryption, the integrity checks, and the authentication, that data is protected. It's the difference between sending a postcard, for anyone to read.
Versus sending a sealed, verified letter that only the right person can open and they know it actually came from you.
Exactly. That's a great analogy.
And a huge part of that verification, that knowing it came from you part, comes down to what you called the digital certificate, right? Often called a website's digital passport, the SSL TLS certificate.
Yeah.
What exactly is that, and why is it so fundamental?
Yeah, the digital passport analogy is pretty good. An SSL TLS certificate is a digital certificate, and it's issued by a trusted third party. We call this a certificate authority, or CA. His main job. Verify a website's identity and establish that trust we keep talking about.
Okay, so what's in this passport?
Inside that certificate, you'll find key information. Things like the specific domain name it belongs to, super important. Also, the website's public key, which is crucial for the encryption process. It also lists the issuer, which is the certificate authority itself, and, critically, the certificate's expiry date. They don't last forever.
Right, and the certificate authority, the CA, you said they're critical.
Oh, absolutely critical. They are the globally trusted entities that validate the identity of websites. They do the checking, then they issue and digitally sign these SSL TLS certificates. Common CAs you might have heard of include DigiCert, GoDaddy, maybe Let's Encrypt. Let's Encrypt is notable because they provide free certificates, which has hugely helped HTTPS adoption.
Ah, Let's Encrypt, yeah. I've seen that name.
Now, sometimes you might bump into something called a self-signed certificate. This is a certificate that hasn't been signed by one of those trusted CAs. Instead, it's signed by the same entity that created it.
So I signed my own passport.
Kind of, yeah. These are typically okay for internal use, like testing environments. But, and this is important, public browsers do not trust them. That's why you'll get a big, scary security warning if you try to visit a public site using one.
Makes sense. Your browser's saying, hey, I don't know who verified this.
Exactly. And one other type worth mentioning is a wildcard certificate.
Right.
This is an SSL cert that secures not just one domain, but all the subdomains under it. So, for example, a wildcard for .example.com would secure www.example.com and mail.example.com and shop.example.com, all with one certificate. It simplifies things for larger sites.
Okay, so these CAs are like the passport offices of the internet, issuing these trusted IDs. But I'm still trying to wrap my head around this. If these certificate authorities are so crucial, what guarantees their trustworthiness? I mean, what if one of them goes rogue or gets hacked? That sounds like it could be a huge problem.
That's a brilliant and very critical question. It's a valid concern. The whole system relies on what we call a chain of trust.
Mm-hmm.
Your browser and operating system come with a pre-installed list of trusted root certificate authorities. Think of these as the ultimate authorities. These root CAs are heavily audited, highly secured organizations.
Okay, so there's a pre-approved list.
Right. Now, if a CA were to go rogue, or if their systems got compromised and they started issuing fake certificates, which has happened, by the way, the browser makers like Google, Mozilla, Apple, Microsoft would react very quickly. They would revoke trust in that CA's root certificate, essentially blacklisting them from the trusted list in future browser updates. It's a system designed to be resilient, though, nothing is ever 100% impervious.
Right, that makes sense. A self-correcting system, hopefully.
Yeah.
So with this system of CAs and certificates and trust chains, how does my browser actually decide in those milliseconds if it can trust a website? You said it was like a dance.
It truly is a sophisticated dance, and it happens incredibly fast. It's called the HTTPS Handshake process. It starts when your browser, the client, sends a message called the client hello to the server. This message basically says, hi, I want to connect securely. Here are the encryption methods, ciphers, and TLS versions I support. Like, here's what I can speak. What can you?
Okay, the introduction.
Exactly. The server then replies with a server, hello. It chooses the best cipher suite they both support and, crucially, sends back its SSL TLS certificate.
The digital passport gets presented.
Right. Now, your browser takes that certificate and does a series of checks. This is vital. It checks. Does the domain name in the certificate actually match the website address you typed in?
Makes sense.
It verifies the certificate's digital signature using the public key of the certificate authority that issued it. This proves it hasn't been forged. It confirms the certificate hasn't expired and checks the entire chain of trust back to one of those trusted root CAs we talked about.
Like checking the passport hasn't expired and was issued by a legit office?
Precisely. And it also checks if the certificate has been revoked, canceled early using protocols like OCSP or CRL.
Yeah.
This is like checking a real-time, is this passport still valid or has it been reported stolen?
Well, okay. Lots of checks.
If all those checks pass, then a key exchange happens. This usually uses asymmetric encryption, think algorithms like RSA or ECDHE. It's a clever way for both sides to securely agree on a secret session key without anyone eavesdropping being able to figure it out. Once that shared secret session key is established, the actual encrypted communication begins, but now using faster symmetric encryption like AES.
Okay, wait. Asymmetric, symmetric, why two types?
Good question. Think of it like this. Asymmetric encryption, like RSA, is very secure but relatively slow. It's great for securely exchanging that initial secret key, like using a really strong, heavy vault door just to pass a small note with a combination on it. Symmetric encryption, like AES, is much, much faster, but it requires both sides to already have the same secret key. So once they've used the slow, heavy vault door, asymmetric, to securely share the key, they switch to using a much faster, lighter lock, symmetric, that uses that shared key for encrypting all the actual website data back and forth.
I get it. Use the slow, super secure method just to agree on a fast secret code, then use the fast code for the actual chat. Clever.
Exactly. It optimizes for both security and performance.
Wow, I never realized how much was going on just to get that little padlock. It's like a tiny, invisible security ballet happening every time I visit a website. So the handshake is this highly choreographed, super fast negotiation, and once they've agreed on all the terms, they switch to this symmetric encryption for speed. But this whole elaborate dance, what's it really protecting us from? Specifically, you hear about man-in-the-middle attacks. How does this intricate process stop someone from just, well, intercepting and maybe reading or changing my digital mail?
That's precisely where HTTPS shines. Its design directly counters man-in-the-middle, or MITM, attacks in several powerful ways. Think about that attacker trying to sit between you and your bank's website.
Yeah, the eavesdropper or impersonator.
Right. Firstly, that certificate verification step we walked through is critical. If an attacker tries to impersonate the real bank website using a fake certificate, your browser will detect it. It'll see the certificate isn't signed by a trusted CA, or the domain doesn't match, or it's expired or revoked, and it will block the connection or throw up a big warning page. It stops the impersonation attempt right there.
Okay, so the passport check catches the fake ID.
Exactly. Secondly, the encryption itself stops the eavesdropping. Even if the attacker can intercept the communication between you and the real bank, all they see is scrambled, unreadable data thanks to that symmetric encryption using the secret session key.
Just gibberish.
Just gibberish. And thirdly, those integrity checks we mentioned earlier detect tampering. If the attacker tries to alter the data while it's in transit, maybe change the amount on a bank transfer request, the integrity check mechanism built into TLS will detect that the message has been modified, and the connection will likely be dropped or flagged as compromised.
So you can't read it, you can't fake the ID, and you can't mess with the message without getting caught. That sounds pretty robust.
It is, and there are even more layers. Technologies like HSTS, which stands for HTTP Strict Transport Security, add another level of protection. HSTS is basically a security instruction, a header, that a website sends to your browser telling it, for the next X amount of time, only ever connect to me using HTTPS, even if the user types HTTP or clicks an old HTTP link.
Oh, interesting. So it forces the secure connection.
Exactly. It prevents attacks called protocol downgrade attacks, where an attacker tries to trick your browser into falling back to insecure HTTP. HSTS basically says, nope, always HTTPS for this site.
Clever.
Then there's something called certificate pinning, which is a bit more advanced. It's like telling your browser, for this specific website, say mybank.com, I will only ever accept this exact certificate or this specific public key. Don't trust any other certificate, even if it looks valid and is signed by a trusted CA.
Wow, that sounds super strict.
It is. It's very effective against sophisticated attacks involving compromised CAs, but it can also cause problems if the website needs to legitimately change its certificate, so it's used carefully, often in mobile apps or high-security scenarios.
Right, trade-offs.
And we mentioned OCSP, the Online Certificate Status Protocol, and CRL, the Certificate Revocation List. These are the mechanisms your browser uses to do that real-time check. Has this specific certificate been revoked or canceled? It's like the bouncer at a club checking an ID against a blacklist before letting someone in.
So it's not enough for the passport to look valid, you have to check it hasn't been canceled?
Precisely. Because a certificate might need to be revoked if, say, the website's private key was compromised or the CA mistakenly issued it.
Yeah.
So checking revocation status is a crucial final step in verifying trust.
It's clear that certificates and this whole verification process are absolutely crucial for trust. But sometimes things go wrong, right? Even with all this, you still sometimes see those browser warnings. What happens if a certificate is expired or invalid? What does that mean for me as a user?
You're absolutely right. Things can and do go wrong. Understanding what happens then is key. If your browser encounters a website with an expired, invalid, or untrusted certificate? Well, first and foremost, it will almost certainly display a prominent security warning or error message. You've probably seen them big screens saying your connection is not private or warning, potential security risk ahead.
Yeah, those scary red pages.
Exactly. They're designed to stop you in your tracks. In many cases, the browser might block you from proceeding to the site altogether. Sometimes it might give you an option to bypass the warning and proceed anyway, usually hidden behind an advanced button.
Which you probably shouldn't click unless you really know what you're doing, right?
Generally, yes, that's very good advice. Clicking past those warnings means you're ignoring the potential security risk you could be connecting to an imposter site or sending data insecurely. Beyond the immediate user experience, an invalid certificate damages trust, hurts the website's reputation, can negatively impact its search engine rankings, SEO, and might even break certain functionalities on the site. So it's a big deal for the website owner to keep their certificates valid and correctly configured.
Okay, so those warnings are serious. They mean something in that intricate dance has gone wrong. That leads perfectly into troubleshooting. What are some of those common digital hiccups, the reasons we might see those warnings, and how can we as users maybe get a clue about what's going on?
Great question. Knowing a few common culprits can be really helpful. Often, your browser itself will give you a hint if you click on that warning message or the broken padlock icon. But some common technical reasons include, number one, as we just discussed, the certificate is simply expired. Website owners sometimes forget to renew them. Yeah, happens more than you'd think. Number two, domain mismatch. The certificate is valid, but it's for www.example.com, and you're trying to reach shop.example.com, and it's not a wildcard certificate. The names don't match.
Ah, wrong passport for the specific destination.
Exactly. Third, untrusted issuer. Certificate was signed by a CA that your browser doesn't trust, maybe a self-signed one on a public site, or issued by a CA that got blacklisted. Fourth, incomplete certificate chain. Sometimes the server doesn't send the necessary intermediate certificates that link its certificate back to the trusted group CA. The chain of trust is broken.
Like missing pages in the passport documentation.
Good analogy. Fifth, revoked certificate. The certificate was valid, but it's been put on that canceled list via CRL or OCSP, maybe because the private key was compromised. And sixth, mixed content. This is a sneaky one. The main page loads over HTTPS, but it tries to load resources like images, scripts, or style sheets over insecure HTTP. This compromises the overall security of the page, and browsers will often block the insecure content or display a warning.
Right. The page itself is secure, but it's pulling in insecure stuff, weakening the whole thing.
Precisely. Those are some of the most common reasons you'll see HTTPS errors.
That's really helpful. It gives you a mental checklist. Are there any simple tools or ways for maybe a slightly more technical user to peek under the hood without needing to be a security expert?
Absolutely. For most users, the best tool is right there in your browser. Click the padlock icon, whether it's green locked or red broken. There's usually an option like View Certificate, Connection is secure, or Connection is not secure. Clicking through those details often tells you the issuer, validity dates, and sometimes the reason for an error.
Okay, so start with the browser's built-in info.
Definitely. Your browser's developer tools, often opened by pressing F12, also have a security tab that provides detailed information about the certificate, the connection, TLS version used, and any mixed content warnings.
F12, okay. Good tip.
If you want to go a step further, there are command line tools. OpenDistal Client is a powerful one. You can run something like OpenDistal Client-connectexample.com.443 in your terminal, and it will show you the site's certificate and details about the TLS handshake. curl with a verbose flag, curl-vhttps.example.com, also shows connection details. And for deep traffic inspection, tools like Wireshark are the standard, though analyzing encrypted HTTPS traffic requires extra setup. Proxy tools like Fiddler or Burp Suite can also intercept and inspect HTTPS traffic, but again, that's more for developers or security testers.
Okay, so options exist from simple browser clicks to more advanced command line tools. That's good to know. And you mentioned RSA and ECDSA earlier, briefly. Can you quickly touch on the practical difference between those encryption methods? Does it matter much to the end user?
Generally, it doesn't matter directly to the end user in terms of functionality. Both achieve the goal of secure key exchange during the handshake. The main difference is efficiency and key size. RSA is the older algorithm, very widely compatible, but it requires larger key sizes, like 2048 bits or more, to be considered secure today, which makes the computations a bit slower. ECDSA stands for Elliptic Curve Digital Signature Algorithm. It's based on elliptic curve cryptography, which allows it to achieve the same level of security as RSA, but with much smaller key sizes.
Smaller keys mean faster calculations.
Exactly. Smaller keys mean less data to transmit and faster cryptographic operations during that critical handshake phase. This makes ECDSA generally faster and more efficient, especially important for mobile devices with less processing power and for busy web servers handling many connections. It's generally preferred in modern deployments.
Got it. Faster, more modern, better for mobile. Makes sense.
Oh,
This has been incredibly illuminating. It really feels empowering to know that with just a few simple checks, maybe starting right in your browser, you can actually get a sense of why a website might not be loading securely or why you're seeing a warning. It truly helps demystify the digital world in a tangible way.
it really does. And just to quickly summarize our deep dive today, we've journeyed through HTTPS, starting with its basic definition as the secure sibling of HTTP. We explored how SSL TLS provides those crucial pillars: confidentiality through encryption, integrity against tampering, and authentication via digital certificates issued by trusted certificate authorities. We unpacked that intricate HTTPS handshake, the dance of asymmetric and symmetric keys establishing the secure session.
Yeah.
And we looked at how all this works together to shield you from threats like man-in-the-middle attacks, bolstered by things like HSTS and certificate pinning. And finally, we touched on how to spot issues, understand common errors like expired certificates or mixed content, and peek behind the curtain using browser tools.
All of this really underscores that HTTPS isn't just some, technical detail buried in the background. It's truly the bedrock of secure internet browsing, the foundation of online trust. And understanding it, even at a basic level, isn't just for tech experts anymore. It empowers you, the listener, to navigate the internet more safely, with greater awareness. It's about being a more informed digital citizen, really equipped to understand the unseen guardian protecting your online world.
Exactly. And perhaps that leaves us with a final thought to consider. As our digital landscape keeps evolving so rapidly, with new threats constantly emerging alongside new technologies,
Yeah.
how much responsibility do we as individual users actually have in understanding these security fundamentals? And looking ahead, what does the future hold for maintaining that essential element of trust online?